Hello, and welcome to this webinar called Can You Trust Your Power Measurements? Thanks for joining us today. My name is Andrea Vinci, and I am a business developer in power electronics and automotive at Tektronix. And today, I'm going to guide you through this webinar. Today, we're going to talk about the challenges of measuring voltage and current, so taking power measurements over fast switching converters, mostly based on wide bandgap components and semiconductors like silicon carbide or gallium nitride. What are the pitfalls? What are the challenges that you may face while taking these measurements? And why you need to upgrade to a new generation of measurement solutions for this. So this webinar is for the design engineers, but also for the application engineers, and also for the test managers that needs to take a decision over a safe and accurate and reliable test setup for this kind of measurements. Today, I'm going to guide you through the measurements that you can take with our new 12-bit oscilloscope platform, the MS05 we have here, but also I will show you our new isolated probe called IsoView, which is an incredible patent from Tektronix that can really grant you accurate measurements in this challenging context. Thanks for joining us, and let's go through this webinar.
Hello, welcome to this webinar brought to you by Tektronix. Today's topic is related to power measurements on fast switching converters. What are the best practices to adopt to avoid pitfalls, and what are the best solutions you can find to ease your daily job? The agenda for today: we would like to discuss measurements requirements for obtaining accurate switching characteristics when testing new fast switching power converters. Specifically, we will concentrate on voltage and current measurements for switching analysis. We will briefly review the relationship between critical circuit and operating parameters and the switching characteristics of voltages and currents during double-pass test. We will discuss the potential influence of the measurement systems on measurement data and what can go wrong when using legacy inadequate equipment. After the presentation, you should be able to identify the most important measurement setup requirements for characterizing power devices and integrated power modules. You should also be able to draw up a more accurate analysis of the economics, the costs versus the benefits and the saving for investing into a specific test measurement solution. You should also have more clarity in projecting the effective impact of a limited capital investment against the hidden operative costs, time-consuming operations forced by inadequate or simply non-optimal test methodology. We will finally show some of the presented solutions in action on a fast switching circuit based on GaN devices. So power engineers, they regulate the flow of power during the energy conversion. So in their end is the enablement of a noble achievement, like reducing the carbon footprint, for instance. But you perceive more the fact that they are really miniaturizing our laptop power supplies and any electronic equipment, making them light and with long-lasting operating time. So power conversion design involves several stages. There is the gate driver stage that translates control signals into an appropriate input for the power switching stage. The power switching stage delivers power to a generic load that depends on the specific application. A low power signal design stage is finally for the control of the system, generally identified as the digital power management or digital power control loop. Some engineers are the first in their company to adopt new chipsets or new switches based on wide bandgap technologies, for instance. And they are sometimes asked whether shifting to silicon carbide or gallium nitride is the right choice. It's basically the right decision for the company to go, and there is no easy answer for that. So for an engineer, adopting wide bandgap technologies and shifting to higher frequency switching means sometimes facing problems that have never been seen before. So silicon carbide MOSFETs, for instance, have high breakdown voltages, allow fast switching speeds, but they also require very careful design to prevent, for instance, unwanted transient oscillations that potentially lead to unexpected turn-on or certainly EMI problems. Also, despite the robustness granted by the reliability test, we want to make sure about the potential overcurrent and overvoltage conditions that might occur in hard commutation and the consequences that this stress can cause over time, especially with the integrated power modules, for instance. And gallium nitride is attractive as well, much lower charges than silicon, enabling very high frequency operation, so very high efficiency and smaller design. And they use the simple half-bridge or totem pole topologies, and these are confirmed basically being the choice for simple and efficient design. But from a measurement perspective, we need to be able to prove that the lower gate charge and the super low on resistance is effective, and to measure the hard switching waveforms that are really fast and sometimes are floating over high voltages. Also, with gallium nitride, we face the challenges of probing very compact packages like SMDs or compact transistors and small drivers ICs. So shifting to wideband gap is not just replacing switches in a long time consolidated design, it's really searching for the appropriate circuit condition to exploit the full potential. It can mean integrating new power sensors, adopting sophisticated power management solutions and new closed-loop control method in order to make sure that the stability is granted. So this might require to seek for the right new passive components, adopting extremely high integrated packages in the PCB, and so improving the layout not just for space or density reasons, but really to solve EMI problems. And what if a problem occurs? So this could mean taking painful decisions, sometimes at an advanced design cycle stage, which can cost the company a lot of money. So in the end, adopting new technologies means inevitably to deal and feel comfortable with uncertainties. And we understand this, and we really want to help out, and at least with the field measurements that you have to take. So, despite the high complexity of the challenges we just mentioned, we still find sometimes customers who are reluctant to invest in the new test equipment. Of course, CapEx investments are in fact immediately visible and tangible and painful, especially when tight budget is assigned. Another clearly perceived pain is the time cost for learning a new measurement technology, since it requires to move from the comfort zone of habits to the learning zone, passing through the fear zone. So what is not perceived at all sometimes is the cost of spending instead extra time in the lab while testing with wrong equipment. And another invisible element is the increase in risk-taking for assuming and guessing rather than proving with real measurements just because the measurement setup is not good enough. So let's start this journey into what matters to power engineers and how to take investment decisions wisely and with a clear awareness of costs and benefits. Engineers today, they require several tools supporting them that already affect budgets. The market is, for instance, introducing ever more sophisticated tools for the automation of design in the design test cycle. And also engineers, they rely on ever faster and sophisticated simulation solutions and hardware in the loop, for instance. And all engineers, they understand how important it is becoming to invest time and money into these simulation stages. But the same should apply when it's time to go to the lab. In fact, a very significant portion of time is spent there, not only preparing the setup and measuring, but also discussing, analyzing, and exchanging a large amount of data with colleagues, suppliers, or customers. So in the lab, there are basically 4 key test areas. The functional stability test, it's basically the problem of converting and controlling the flow of energy has basically to be solved, and the circuit should work under several load conditions and operating conditions. The losses and performances, it's about a perfect characterization of what happens during the switching event in order to grant the overall performances of the system. The thermal management means basically making sure that the amount of waste heat generated is compatible with the size and weight constraints of your project, as well as the operating ranges of your switches. And finally, the EMI and noise filtering. Basically, you need to identify all sharp corners, transitions, oscillations, and overshoots and undershoot spikes during the switching transitions and determine whether, I don't know, passive filtering is enough for you, or if you need to intervene at the control stage, shaping the gate driver, for instance. And all these measurements, all these phases, they require investments. So, something like, okay, upgrading to a new oscilloscope must really come with really good reasons. Let's see what we can do in this sense. When it comes to performance measurements, there are generally two aspects to measure in order to prove that any action has an impact on the overall efficiency of the conversion system. We can say that losses on switches derive from the existence of a non-zero resistance in the conduction mode and from the losses during the switching transitions. So the first thing to measure is how much is the DC power absorbed. The second is to investigate how much are the energy losses during the switching events. And this is easily obtained by a multiplication of VDS and ID, for instance, voltage and current. That means that we need an oscilloscope and some probes to measure voltages and currents and calculate the power switching loss with a simple math multiplication function. If you want to obtain the energy, you simply integrate the power curves between two instants, the one initiating and the one terminating the switch. Regarding the first point, so the losses during conductions, they depend on the so-called on resistance of the switch. The shift to wide bandgap technology has made more difficult to model with circuit simulators like SPICE or others. So the RDS on values might vary according to the switching condition of the power converter. Especially this is true for gallium nitride device. It is so really important to compare modeling results with the real accurate measurements. We may also want to appreciate, for instance, a trapping effect called the current collapse. That means that when the RDS on increases while switching from what we call the typical value that you characterize in DC. So the variation is a function, for instance, of the applied DC bias voltage when the device is in off state. And this also depends on the time which the device is biased and the operating temperature and other factors. So this measurement is again something you can see from voltage and current measurements on an oscilloscope. But today, wide bandgap semiconductors like gallium nitride, they present the RDS on in the range of very few milliohms or less, while the existing equipment that you may have in the lab was used for semiconductors having hundreds of milliohms RDS on. So is it still valid? The voltage drops are getting smaller and smaller and smaller, and even if the switching current increase, the resolution of a standard 8 bits or 10 bits oscilloscope may no longer fit today. This use case with gallium nitride makes immediately visible the difference of using new 12-bit ADC technologies and increasing the vertical channel sensitivity. The noise of the preamplifier, the linearity of the whole circuit, and the effective resolution of the ADC converter have a significant impact on what you see on the screen and what you can present in the measurement report. The TEC49 is a Tektronix proprietary ASIC and the product of the largest ASIC investment ever in Tektronix history. It is basically the core of the MS-05 series oscilloscope, and it is what gives the oscilloscope the high resolution capability as well as several other features. So the resolution of the scope is another key factor to keep in mind. Now let's consider the second point, the losses during the switching events. The most typical lab test circuit configuration for measuring this switching characterization is the double pulse test setup, or the DPT. This is common across all power electronics engineers, and it's generally used as the switch element level for what we call the dynamic switching characterization of the power devices. But the double pulse test is also used at the power converter system level for the overall evaluation of the efficiency. In this case, the double pass test layout has to be very, very similar to the layout of the final converter. And it is also obviously present when a gate driver stage needs to be characterized. So usually the test board is a modular test board separating the power stage from the gate driver. So let's assume then for this webinar that you are performing your switching loss measurements over a double pass test board or a similar setup. The double pass test is used to observe all waveforms during the switching transient of transistors without basically having to hit the devices too much. Usually engineers choose a load inductor, adjust the first pulse to turn on the lower transistor, and therefore they charge a current through the inductor to the magnitude that basically they are interested to analyze. That's the phase 1. And then they take a short break, which is the phase 2, and they start sending a second short pulse to analyze the turn on and off phases of a hard switching transient at the desired current level. So let's assume that this is the kind of setup that you need to reproduce in your lab and that you need to decide how to choose the best solution for the highest investment return in terms of testing equipment. So in your converter design, or if you want in the double pass test board that reproduce it, the parasitic impedance minimization is a must. There are mainly 6 parasitic parameters, as you can see from the scheme on the upper right, including LGS and CGS in the gate loop, LDS and CDS in the power loop, and the mutual parasitics, LCM, and the Miller capacitance, the CZD, shared by the gate driver and the power loops. So among them, the power loop inductance, the LDS, and also the common source inductance, LCM, and the Miller capacitance, the CZD, they all significantly impact the switching performance of fast switching wide bandgap devices. The power loop inductance is basically the biggest contributor to the power loop ringing and the overshoot voltage, and this is also causing EMI and also potential reliability issues. And the mutual parasitic and the Miller capacitance, they work as a sort of negative feedback from the power loop to the gate loop during the transients. So they lead to slower switching, and they increase the switching losses basically. So anything in the circuit contributes to these parasitics, including the MOSFET source lead pin length. So everything really. The VGS measurement, for instance, might be affected by the voltage created on the inductance by the transient of the current on the pin. So this is the reason why some MOSFETs have a Kelvin connection lead. So the layout, the routing to reach the test point on the board for connecting probes also matter, because if you routed your gate pin through a lane around the board and through vias in order to reach an area where you had enough space for placing a test point, that might affect your measurement since it increases these parasitic values. So for this reason, we recommend with wide bandgap devices to find solutions that allow you to connect straight to the device pin. So why are the effects of parasitics so bad? Let's see some typical challenges when measuring switching characteristics, and let's imagine a typical high voltage setup with the DC link between 600 volts or 1 kV, and the VGS with a moderate swing between generally -5 and +5 volts, for instance. So during the turn-on phase, the VGS reaches the threshold voltage, and the ID then starts to increase linearly from 0 to the load value, and the VDS switches very fast from high to low. Then the voltage drop across the parasitic inductances and the inductive load, they often cause a sort of reshape of the VDS voltage during this switch. It's a sort of notch, and the ID current peak also might be affected by ringing. So measuring this can be a challenge today without the right test solution, because what is the ringing telling me? Is it real? Is it accurate? And the same thing is for the turn-off phase, because the parasitic will cause a significant VDS overshoot during the turn-off. And it is important for us to measure it because it sets a sort of constraint over the DC input voltage, the maximum breakdown voltage rating for the module or the switches that you use. And the overshoot measurement is important because it's also an input data for your EMI mitigation actions and is a KPI to consider when estimating the reliability and the duration of your switches over time. So all these measurements are really important. And you need also to know if you need to apply some clamping, for instance. So maybe you have to redesign something. Is it this ringing only because of the energy stored in the parasitic inductances in the power loop? Is it something else? So when you see the ringing, you must recognize if the overshoot is caused by the effective circuit parasitic loop inductance, or eventually estimate also a contribution from the measurement system. And the same for the VGS. The gate loop with parasitics, the LG and the CGS, which forms a series circuit, they often shows ringing during turn on and turn off. So to estimate the losses and verify the functional requirements of the gate driver stage, you really must be able to improve what you can see on the screen. And these are lower voltages to measure, so you need a high resolution. So let's jot down the following conclusion. The parasitic minimization at the board layout level as well as the measurement system level is key to improve your measurements results and to minimize redesign actions to correct potential failures that may not be as big as you would expect. Now, let's assume that you designed your totem pole double pass test board very wisely and minimizing the parasitics. So how do you improve further your system? But basically, you then want to push it and you want to prove that it's good for switching very fast, okay? But when you switch fast, the bandwidth of the signal is obviously larger, and wideband gap devices, we said that they have a high-speed switching transient. The rise and the fall time are generally defined as the settling time to reach the 90% of the steady-state value. So to capture them, your 200 megahertz oscilloscope might not be able to capture it anymore, especially if it is combined with the high voltage probes that usually have a bandwidth which is often limited to 50 megahertz or 100 megahertz. So there is an important question: how much is the bandwidth that you really need? Well, it's a simple calculation to do, coming from signal theory. There is a formula giving you the effective bandwidth of a signal with rise time TR and a fall time TF. And once you get this number, the whole system bandwidth should be 3 or 5 times higher than the maximum equivalent frequency of the measured signal for the magnitude, and much more for the phase. So when your rise time or your fall time are generally below 10 nanoseconds, you enter a sort of danger zone of inaccuracy with your existing test system built around a 200 megahertz reference bandwidth. So Tektronix, the new differential probes, electrical differential probes, they have 200 megahertz of bandwidth, and if you match them with a 200 megahertz oscilloscope, the rise and fall time you can capture cannot be less than 9 or 10 nanoseconds. But the typical silicon carbide MOSFETs used in applications like renewable energy or the EV, electric vehicle battery chargers, or the DC-DC converters and power supplies, also up to 1 kilovolts, the VDS rise and fall time, they may range generally between 4 to 8 nanoseconds. So to capture this with fidelity, you need to shift to 500 MHz oscilloscopes and probes having at least 350 MHz bandwidth or more. So for ground reference measurements, where you can basically use a passive single-ended probe, there is no big deal. So Tektronix had since a long time 1 kilovolt differential probe, the P5200A, which had 50 MHz bandwidth but could accurately measure a 14 nanosecond step signal rising time with 1% error. And then, of course, we evolved. We had the new P5000 series up to 2.5 kilovolts that were able to capture down to 3.5 nanoseconds with their 500 MHz bandwidth. But today, there is a special jewel for high voltage passive measurements, the TPP 0850. And this is a 2.5 kilovolt probe with 800 megahertz. It's an outstanding bandwidth, so the rise time can go down to 2.2 nanoseconds and can be captured for high voltage switching waveforms in combination with the 1 gigahertz bandwidth oscilloscope like the MSO5. Things gets even more tricky with the gallium nitride device, and for the gate drivers, the VGS switches at 4 or 6 nanoseconds, and the VDS can turn on and off in the high voltage space, which for GaN is 600 volts, sometimes with faster edges. So we may need to go even lower than 2.2 nanoseconds, and the Tektronix here has a unique solution with the passive probe, the TPP1000. It's the only passive probe in the market able to capture less than 2 nanoseconds rise and fall time with its 1 gigahertz bandwidth. So ground reference measurements need to obviously reach ground. Looking at the double pass test board, there is a ground plane on the board, and all power design engineers know that assuming every part of a ground plane of the circuit under test being actually at the same potential is essentially wrong. So not everything is tied to the same ground in the circuit, same for your measurement system. There are other grounds connected, like the one from the power supplies, for instance, that can reach out to the double pass test board using long leads, so with parasite inductances. And this and any other auxiliary power supply that you connect to the board can create coupling loops to ground. So these loops may cause resonant ringing and common mode current overlapping to the drain current, for instance. So now consider that you are connecting to your circuit your ground lead for passive probe, and there is the scope input which is tied to the earth ground. So depending where you place the earth ground of your oscilloscope through the passive probe connection, you influence the ground loop in your circuitry and therefore your measurement. So any piece of wire has a distributed inductance that reacts to the AC signals by basically increasing the impeding AC current flow, and this increases as the signal frequency increases. So the ground lead is no different. It is really a piece of wire, and its inductance interacts with the probe input capacitance, creating a series resonant network, which is in combination with fast signal transitions. Basically, you stimulate oscillations. As the series resonant circuit experiences a sort of pulse, however you capture it, you have a ringing, and the frequency is related to the grounding lead length. So the ground lead inductance also suppresses the charging current to the input capacitance and limits the rise time of the pulse signal. And this is also affecting your measurement. So you need to take care about the ground lead length and the probe input capacitance, and to minimize the size of the loop to avoid capturing disturbing signals. So to reduce the ground lead inductance, I have seen the most creative ways of custom-made pigtails when the choice is to solder the tip directly to the board. Or as an alternative, I've seen the use of various different PCB probe tips adapters. Tektronix TPP1000, the only 1 GHz passive probe in the market with only 3.9 picofarad input capacitance, it also comes with a whole set of adapters to minimize potential loops and parasitics caused by the ground lead. And I'm not referring only to the spring clip, but to a whole set of coaxial adapters like the MMCX connector, which is a low-cost, small industry standard coaxial adapters that are recommended by several semiconductor suppliers for this kind of measurements. Let's talk about measuring currents, which is a key problem now with wide bandgap devices. Several current measurements techniques are existing for the ID measurements. You can use coaxial shunts, you can use current transformers, Hall effect probes, Rogowski coils. But you need to be aware that each current measurement technique will introduce additional parasitic inductance in the power loop, and therefore it will affect the switching phase. So depending on the specific solution and the situation, you might choose a different way to measure current, but you also need to be aware of the pros and cons of the solution that you choose. You might be aware of the low bandwidth and the low accuracy, for instance, of the Rogowski coils, and even if sometimes it's the only way to probe a very slim press-fit package pin without breaking the circuit. Our all-effect sensors probes like the Tektronix TCP0038 are great, essentially are a standard in terms of accuracy and sensitivity, but they won't be able to take you in the space of less than 10 nanoseconds switching time, as we have seen before. So, to grant both the bandwidth and the accuracy, it's inevitable to shift today to indirect measurements with the coaxial shunts and voltage probes. In this way, you basically get the accuracy, you get bandwidth, and the high current measurement range at the same time. Of course, at the expense of having to find space on the PCB for these shunts. So remember that adding a shunt also means adding a parasitic inductance. So shunts nowadays are going under a deep redesign, exactly to keep their size very small and the parasitic inductance very small. We can recommend you several solutions for shunts to be used in combination with our voltage probes, because not all shunts may fit any design. When you need to measure the voltages on the high side stage, you are in a much more difficult measurement conditions. You are off ground. In this case, you need galvanic isolation to take voltage measurement. So is the probe voltage and bandwidth ratings the only requirement to meet in this case? Well, obviously not. In this case, with galvanic isolation, you also need to grant also high common mode rejection. No electrical differential probe today has the combination of bandwidth and common mode voltage and common mode rejection needed for testing fast switching converters. Voltage and loading and CMRR, they are all values that derates over bandwidth. And the long leads of this probe make the probe susceptible to noise and to radiated emission as well. So this means that the waveform shape changes based on the lead length and the position of the probe and so on. And also the probe is susceptible to ground loops, as we have seen before. Tektronix ISOView instead is basically the only answer in this case. It is the result of the combination of finest measurement technologies and a deep understanding of the new measurement requirements for fast switching systems. This is the must-have tool for all circuit designers who really want to optimize their design performances. This probe is essentially designed to grant high common mode rejection ratio across a very large bandwidth, up to 1 GHz essentially, because it's an optical probe completely shielded down to the probe tip. The amplifier is powered over fibers, so no batteries nor power supplies referenced to ground are in this probe. And the probe itself is designed to add the minimum load burden to the circuit, as we will see in the next slide, also to optimize the connectivity to your circuit with a long list of special new type of leads. So do not underestimate that also a purely optical probe with up to 10 meters fiber length is essential to operator safety. Safety is very important, especially when measuring high voltages like 5 kV differential voltage over 60 kilovolts of common mode voltage or higher. So think about these situations. Differential voltage probes leads have usually standard large hook clips that are basically inadequate for dense environments, and also they lack performances. Switches and drivers are offered in many different packages, as you can see in this slide. So why probes should not offer different connectors then? Tektronix ISOView offers a range of connectivity solutions with the key advantage that also the probe tip is completely shielded. The best practice of twisting probe leads may no longer be sufficient when high voltages and currents are swinging so rapidly, like with wideband gap components. And the common probe leads are anyway picking up some signals. So you will really get rid of any oscillations by considering a wise use of this new optical probe with these new shielded leads with the very special connectors adapting to several situations. Let us support you finding the best way to probe your system in a safe and accurate and reliable way. So here in this picture, you have a few pics related to real use cases you might be interested to see and eventually find similarities with what you are trying to do, but we can design something custom for you as well. All right, so now we know that we need in terms of scopes and probes and connectors and leads and so on. So let's finally perform the calculation of this energy loss during the turn on and off phase. So we have seen that for this calculation, you need to be able to clearly see the signal to identify the right timing reference. But another potential error you can commit comes from the misalignment of voltage and current during the measurement. So consider a gallium nitride devices, for instance. So the switching loss energy, even at, I don't know, 500 volts or 600 volts with tens of amps, are in the range of tens or even few, even less microjoule. So very, very, very few. So can you accurately test the microjoule order of magnitude switching energy in the same way that you used to measure millijoule with IGBTs, for instance? Again, obviously not. So when you are competing to prove your outstanding efficiency range is around 99% or more, you really want to be extremely accurate. So think about the error that you may commit if voltage and current are just minimally skewed when calculating such a small overlap area for the energy. So each of the voltage and current probes have its own characteristics propagation delay, and the skew between these two delays will cause inaccurate measurements of switching losses, typically for fast switching wideband devices. So in the past, engineers were choosing voltage and current probes with similar propagation delay in the range of tens of nanoseconds to minimize the error on switching loss, but this is no longer acceptable. It's important here to have a standard automated way to avoid the voltage and current misalignment. So some users perform a visual manual skew, adjusting directly with knobs the waveforms on the oscilloscope, and they align the voltage drop of the VDS to the point where the current turn-on transients begins. But what if you have a ringing or noise in the signals? So these methods becomes really impossible to implement, or even worse, for those who still do it, this can lead to totally wrong results and no measurement repeatability. Tektronix oscilloscopes, instead, they offer an automated procedure taking into account each probe's specific propagation delay and compensating it by simply pressing a button. This is also critical because probes, like differential electrical probes, they change their propagation delay when you change the dynamic measurement range while you use it. So please remember to run your DSQ procedure only once you set the range operating conditions that you need to set for the measurement. And finally, Tektronix oscilloscopes, they offer an automated software to generate easily a measurement report as well as exporting session files, and this allows you to easily share the raw data, the setup, and everything needed to replicate and to review the numbers with extreme ease and precision, including the compensation of skew that you may have manually added. Let's talk about gate drivers now. Gate drivers generate the necessary voltage and current level required to precisely activate the switching power stage of power converters. For some industrial or automotive application, the gate driver IC has to be also galvanically isolated for safety and also for functional requirements. So designing a gate driver board and finalizing the design of a gate driver IC requires to be extremely accurate in measuring the VGS rise and fall time, the source and the sink current, as well as selecting the pull-up and the pull-down resistance. For this reason, gate drivers designers are heavy users of instruments for double pass test. Aside the voltage waveforms and the control bus timing correlation for functional verification, there are two critical factors to measure that are basically the common mode transient immunity, the CMTI of the gate driver isolation, and the crosstalk suppression. So the CMTI is a typical measurement taken on isolation between circuits. CMTI requires to verify if applying a high voltage transient on one stage, this causes some effect on the output voltage, and to accurately quantify how much this effect is. So is the galvanic isolation test good enough with voltages around, I don't know, 2 kV to 6 kV, depending on package, and the CMTI, the dV/dt, is more than 100 volts per nanosecond. So you need to make sure that you have the right measurement tool allowing you to perform a CMTI test analysis of your circuit, and this tool should reject common mode noise as well as as well as the circuit, because otherwise it would be completely useless. So let's talk also about the crosstalk suppression. So this is more related to what we call the Miller effect. The Miller effect is quite easy to explain. It's a mutual crosstalk effect in a half-bridge setup configuration. It occurs basically when the dV/dt during the turn-on transient, for instance, of one device generates EMI and also a current flow through the Miller capacitance on the other MOSFET. So this current somehow reaches the gate loop and generates a positive voltage spike on the gate. And of course, if this spike is high enough, it may happen that the effective device turns on while the other is on as well, causing a shoot-through current from the DC bus to ground. Likewise, a negative spurious voltage on the gate is generated in the synchronous device at the turn-off of the control device. So when this phenomenon does not damage the circuit, it for sure worsens the switching performances. So it's really important to avoid it. So you may think that this is not a big deal since wideband gap devices like silicon carbide, for instance, have a very, very small Miller capacitance compared to silicon IGBTs, for instance. But unfortunately, the switching speeds are also much faster and the threshold voltage are lower, so designers are still struggling with this phenomenon. And this is getting critical for those designing the gate driver boards intended to be used with gallium nitride switching stages. So let's see more about the measurement problem. Alright, so how does a design engineer control noise coupling from power to gate drive loop when the dV/dt and the dI/dt are very high and the input capacitance, the CISS, and the gate voltage threshold are very low? There is hard work of design to protect the gate from spikes and oscillation, since the mitigation will come from what we call the active gate driving techniques. But these techniques, they compromise on performances, and the use of extra snubbers, for instance, or ferrite, are also compromising on performances. So we really want to make sure we do not overestimate or over-design. So you want to invest into the best probing solution to clearly characterize the behavior of the gate driver during the operating conditions. As you can imagine, only a very sensitive and sophisticated instruments can detect a phenomenon like a crosstalk effect or validate the common mode transient immunity. These instruments should be itself immune to the crosstalk first, in order to reveal only what is occurring on your circuit. So a standard voltage probe may not be clearly sufficient. And also a small differential voltage needs to be measured on top of a floating high voltage, sometimes kilovolts, with a very fast voltage swing. So a probe that accurately measure this kind of phenomenon that has to be sensitive, has to be accurate and immune to disturbance noise, and must have a very high common mode rejection ratio across a very wide bandwidth, because this is imposed by fast voltage swings. So again, there is no such thing in the test and measurement world except an extraordinary solution patented under the name of ISOView technology by Tektronix to do that. And our solution has been endorsed by several semiconductor suppliers working in this application space. Alright, so let's complete this part by talking about other DC voltage measurements. For instance, measuring the DC bus link. The DC bus is an essential component of systems because it enables the power transmission between the sources and the loads. In automotive application, the batteries, for instance, are the sources and are interfaced with the bus using a charger or a discharger DC-DC converter, which is controlled to regulate the DC bus voltage under any operating conditions. So this is an important task because unsafe overvoltages and undervoltages in the bus could damage the sources and also the loads and the power converter as well. So the bus regulation requires bus voltage measurements taken in a safe way and with high disturbance rejection. So again, in a double pass test setup, you have, for instance, a DC capacitor which is used to stabilize the DC bus voltage across the phase leg. And when designing the DC link capacitor stage, there is always a compromise between the size of these capacitors and the acceptable ripple current. So it is important to measure the ripple current capability of your DC link capacitors, the voltage ripple coefficient, and sometimes we are talking about 1%. So if you measure the current, you may be using a Rogowski coil or a high current probe like the Tektronix TCPA 300, but this may not give you the high resolution data that you need. So you need to use something different. You need to use the right probe with an attenuation factor that allows you to best fit the accuracy range of the oscilloscope. So in the electric vehicle market, the DC link can be 400 volts or 700 volts or even 920 volts or 1 kV. So you may need to measure these voltages in a galvanically isolated way in accordance with your safety regulation, your internal safety regulation, and you may need to grant the ripple on the bootstrap power supply voltage at the high voltage DC link. So again, this is a typical case where the ISOView probe can easily support you with the high voltage tip adapters. It's a small investment for a total safety compliant and high accuracy solution. What about the DC links in the low voltage space? In the low voltage space, we call the DC voltage supply, we call them the DC power rails. They can be 48 volts or 24 volts in the automotive space of mild hybrid, and they are basically the intermediate bus converter DC voltages. The DC rail voltages can be anything down to 15 volts, 12 volts, 5 volts, and also 3.3 volts for point of load regulators. But they can go even lower. They can be 1.8 volts or 1.2 and even 0.8 volts at very low power ICs and circuits. So measuring ripple on 0.8 volts poses completely different challenges than taking it at the 48 volt, for instance. So you may want to really make sure your probe allows you to maximize the dynamic range capability offered by your scope, for instance. So Tektronix offers an active rail probe with up to 60 volt offset and 1 volt dynamic range and up to 4 gigahertz of bandwidth. So it's a high resolution rail probe, but again, this is not enough. What matters to power engineers are also the possibility to support connection options to cover several scenarios. So this is why Tektronix not only studies the scope and the probes, but also provides various solder-in tips or adapters for sensitive signal connections like SMA, MMCX, or UFL, square pin, in order to connect to the test point in the best way. So the recommendation here is really to consider 3 aspects: the combination of the probe with a real low noise oscilloscope front end, because in fact it's the combination of the two that gives you the overall amount of the additive noise that you are bringing to the system; the connectivity option, that is very important to avoid the degradation of the signal; and also a software part, because the solution should be offering automated measurements application to speed up your test time. So this is really important, and Tektronix is offering all these in a sort of combination of setup between software and oscilloscope and probes. The power rail probes, they are really no noise. They have a large offset range, measuring a ripple on DC power rails ranging from -60 to +60 volts DC. And we also offer the industry-leading low noise and high offset range required to measure ripple between 200 microvolt peak-to-peak or up to 800 millivolts peak-to-peak, up to 4 gigahertz of bandwidth.
Time for the live demo now. We have been through several topics during the webinar, several theoretical concepts and practical things to do. So now let's see them live on a real demo board. In fact, here I have a demo board with the gallium nitride devices in a half-bridge configuration, which is what we have discussed before, and we want to test a little bit the switching waveforms of voltage and current here. So let's go through the best practices that we discussed about. First of all, we mentioned about the potential problems caused by the ground loops. So here is a typical probe configuration with this long tail, and we discussed that there is an inductive effect from the ground tail here. So what can we do about it? As we have seen, we can simply modify this probe by replacing the tip that we have with the tip that implements the coaxial MMCX connector that we discussed about. So you just screw it in, and here we go. Our probe now is ready with the minimal ground loop possible. So there are several semiconductor suppliers that are offering, for instance, these connectors as test point on their demo board. And this is quite easy to do it because you just plug it in and it sustains the weight of the board. And it's very easy to plug and unplug it, okay? This is much, much better than using even a small pigtail and soldering down on the board. So what we have just seen allows us to use the TPP 1000, the 1 GHz passive probe from Tektronix with this special connector. So we can benefit from the super fast rise time and fall time capture for less than 2 nanoseconds with this connector without problems of ground loops. Now, let's see why this is important. So we discussed about the effect of leads of typical differential voltage probes like this. These are the standard electrical differential voltage probes. And as we discussed, the problem is that the leads are not shielded and they can add parasitics to your circuit now that you are using these sensitive devices. And even if you twist your leads, that's not enough to avoid coupling of signals into your measurements that can cause ringing and affect the accuracy of your measurement. So how do we solve the problem? Well, as we discussed, the ISOView probe presents a completely different new type of lead. This is a typical tip for the ISOView probe, and as you can see, we can offer different connectors. The one that you can see on the board are designed for connecting to the MMCX adapters, but we offer also square pin adapters so that you just need to solder down a simple strip line to your circuit, 2.5 millimeter spacing, and then you can just plug in the tip and connect it. That's very, very easy. The good thing of this tip is that this is shielded with ferrite all the way down to the tip, allowing you to protect your measurements from the noise of the environment. Another important thing that we have seen about the tips is the fact that they load your circuit. So the capacitive load is really, really important to consider. These tips have very, very low capacitive load, meaning in the range of really 2 or maximum 3 picofarad, even at the high voltage range. Another key topic that we have seen is the importance of respecting the ratings of the signal. Now with the fast switching devices, the rise and fall time goes way below 10 nanoseconds. So, the usual bandwidth, 200 MHz, 350 MHz, may no longer be enough. You may really extend the bandwidth of your measurement system. But by doing this, you need also to respect several other constraints, like for instance, the common mode rejection ratio. This is why we presented our ISOView probe, which has the ability to see signals with extremely high bandwidth in a galvanic isolated way. I mean that we can measure high voltage signals up to 5 kilovolts peak to peak over a 60 kilovolt common mode signal with 800 megahertz of bandwidth. And the common mode rejection ratio doesn't really degrade too much with the frequency, protecting the accuracy of your measurements. The same thing applies to the model of the IsoView probe that fits better for low voltage switching signal, especially when you need to probe and measure the gate voltage, for instance. In this case, we have the possibility to have even 1 gigahertz of bandwidth. We have seen that we offer plenty of solutions for probing voltages that switches really fast, so below 10 nanoseconds. We have passive probes, we have high voltage passive probes, and we have this differential optical isolated probe that we patented. So the importance of this is immediately visible when you need to capture the fast rise and fall time on the screen of your oscilloscope. Let's consider now another best practices. So we discussed about the importance of considering the skew. What is the skew between the signals that you see on the scope? It matters because it refers to the propagation delay of the signal along the probe from the test point into the oscilloscope. So we have seen that it's really important to consider this, especially when you measure the switching loss, because if the voltage and the current are not perfectly aligned, you may have a significant error, especially with such steep rate of change for voltage and current, because the error becomes bigger and bigger. So it matters to the skew the probes that you have connected to your scope. And with Tektronix, you can do that automatically because this is quite a very easy procedure to do. You just press your channel, you double click and you go into the other menu, and here you see that you can perform an automatic skew compensating for the propagation delay of each probe connected to the front end. This is in fact possible because the oscilloscope can read from the probe the propagation delay of the signal and make sure it compensates for it. So we respect signal ratings in order to capture such fast rise and fall time. We improve the way we connect to the board, to the test point, avoiding capturing noise. We minimize the loops, the ground loops, the parasitics that we had to the circuit. And these are all best practices. Now it's time to look into the scope, and we have seen that it's important to the skew channels and propagation delay to be considered for the probes. We need, of course, to follow the usual best practices, compensating the probes, okay, for instance, making an auto zero, waiting for at least 20 minutes until the system is warm up. This is really to minimize any potential error on the measurement. And then we are ready to go. We are ready to see our waveforms on the scope and take our considerations. Of course, following these best practices and using the right products, especially this IsoView probe, you can clearly see the signal on the screen not being affected by too much ringing because of the parasitics or because of the signal coupling and the noise, as we have seen. And this allows you to take your measurements with ease. So let's see a little bit what to do with this waveform and how to take these measurements. It's quite easy, as you can see. For instance, here on channel 2, the blue line, you can see the gate source voltage, the VGS. And you can see the Miller plateau clearly. This is something that is very hard to capture. If you want to measure the duration of the Miller plateau, you just need to place cursors on the screen and you can move them along the waveform in order to measure the duration of this. And this is quite easy and straightforward to do. If you want, for instance, to measure the dead time, okay, between the high side and the low side VGS, it's also even easier. In this way, for instance, you have two different swim lanes for the waveforms, but if you want to see them overlapped, you just do this and you move one channel onto the other, and here you can see that the two waveforms are overlaid on the same lane so that you can clearly see and make your measurements in this easy way. There are already several videos on our website explaining in detail and digging into the ISOView probe, so I'm not going to repeat that, but there is one thing that I want to point out here because I think it's really, really important. So there are several aspects of this probe that I like and that I presented during the webinar. The shielded tip, for instance, the fact that there are no amplifiers in here, it's powered over fiber, the fact that it's galvanically isolated, and so on. But there is one aspect that is safety that for me is really important. When you have to test the high voltages signal, you must be safe, okay? So the optical isolation is really important, and this fiber can be as long as 10 meters if you want. So you can keep your device under test very far away from the point where you operate with your instruments. Now, very briefly, let's talk about current measurements. We have seen before that current measurements are even more challenging because the sensors that we find in the market are basically, in general, for slower switching currents. And now you need to capture fast currents with the wide bandgap based power converters. So the idea here is to see a little bit why it's important to move to indirect measurements of currents, because using, for instance, a shunt to convert the current into a voltage, you can benefit from all the advantages of using, for instance, an isolated voltage probe for taking fast switching current measurements as well. So here, for instance, we have in this board, these two parts are replicating basically the same circuit. So on the upper side, we are measuring the current through a shunt. It's a 1 ohm resistor, and we are connecting it through an MMCX adapter to the voltage differential probe. And we are seeing the signal over here. There's a bit of ringing, okay, of course, but not too much. On the other side, we are measuring the same current using a loop here through the square pin adapters and connecting our typical Hall effect current probe. Here you can see much more oscillations. So this is because, of course, of the fact that you are using this loop, and this loop is adding an inductance, and it's also somehow affecting the current as well, slowing down the transition. So it's really important when a transition is fast to consider what is the best way, the best solution to use for the current measurement as well, and indirect measurements might be the answer. So another important point is how much time do you spend on your measurement? And I'm not only referring to the fact that you may be trying to fix artifacts of the measurements that are not real problem on your power converter, and we have seen how to avoid this by choosing the right test equipment. I'm really talking about the practical aspect of taking the measurements, of moving knobs and cursors around your oscilloscope screen in order to prepare your report and send this data out of all the stakeholders involved in the power converter design. So wouldn't it be much better if the oscilloscope would do all this analysis for you? That's what happens with Tektronix application software. There are several application softwares that you can find for the oscilloscope, for any kind of measurement, but in particular for power electronics, we have something interesting for you because we can perform the switching analysis, all the calculation of the energy losses during the turn on and turn off automatically for you, creating a report that is very nice and easy to send and to correct and to report this to anyone interested in the measurements. One last point here. We concluded our webinar talking about DC measurements on DC link, high voltage DC links, but also low voltage DC power rails. So I really care to show you our Tektronix power rail probe with 4 GHz bandwidth. So this probe is an active probe that allows you to measure the ripple on the lanes, on the power lanes. So here, what I did was simply using this board. This board receives the power from the USB port of the scope, and then upscale the voltage up to 50 volts, something around 50 volts. So to make sure how much was the offset that I should correct with our rail probe, I used the passive probe here to measure exactly with the digital voltmeter functionality of the scope how much is the voltage here, and it's about 50.2 volts. So I applied that to the rail probe channel, and here I can see the ripple on the waveform. So this is the 50 volt lane, the power rail that is supplying the DC voltage to the setup, to the circuit. So we see a lot of ripple here, and we see also some sort of spikes, and these are related to the fact that there are switching elements here. In fact, the spikes are exactly corresponding to when the switching occurs. If you want to perform a frequency analysis of the ripple and anything that is coupling into the power rail, you can simply turn on the spectrum view on the oscilloscope. And this spectrum view allows you to perform the spectral analysis of the signal in a way that is completely disconnected from the time-based setting. This is a specific patent of Tektronix, and it's called spectrum view functionality, and allows you really to make sure that you have a detailed and accurate frequency domain analysis of your signal. That concludes our webinar for today. We have seen that wide bandgap-based power conversion design requires to adopt new measurement technologies to have accurate results. We basically learned three main things. Respect your signal requirements, not just for the bandwidth or for the voltage and current ratings, but also for other aspects like common mode rejection ratio, for instance. The second point, take wise decision on your test point and make sure that you don't create ground loops, for instance, with your probe leads, in order to avoid to spoil your measurements with this kind of parasitics effects. And third, make sure you use automated test tools, because this can really speed up your test time. You can avoid wasting time with knobs and cursors placing if you can rely on a scope that does it for you. That's it. For further information, you can look into our website. There's plenty of material, application notes, and videos that you can see. But better to call us for a trial, invite us for some discussion on your challenges. And remember, we are Tektronix, we are for you, and we are for the engineers. Thank you.